Hello everyone, welcome back to this week's algebraic graph series seminar. This week we have Alison Marr to tell us about the distance magic labeling on directed graphs.
Thank you. Thank you for the invitation. I was really excited to get to come talk about some of the questions I've been working on recently with a couple collaborators and some students that I'll introduce later. I wanted to start with a disclaimer, I guess. Maybe I am not an algebraic graph theorist. I'm going to try to, in the first couple of slides for you all, frame for you maybe why an algebraic graph theorist might be interested in these questions so that you kind of have an angle that you might be interested in thinking about as I talk about the work that I do. So that's kind of what I'm going to start out with as we get started. I will say that I'm working with oriented and or directed graphs, and we'll talk a little bit about how I distinguish those. Usually simple graphs with n vertices and m directed edges. When I talk about an oriented graph, I'm talking about where there's no repeated edges, in particular that you can only have a directed edge between two vertices. You can't have an edge in each direction. So you can't have those bidirectional sort of edges. And then for directed graphs, I will allow for those bidirectional edges. So we'll have situations where I'll sometimes be talking about an orientation that I place on an underlying graph, right? That's a simple graph that then has edges directed in one direction or the other. And then there are other situations where I might be talking about labeling a directed graph, which allows for that opportunity to have those bidirectional edges. So to give you a little bit of background on the problem, sort of where this problem sort of originated, this is a definition from 2003 from Miller, Roger, and Simon Juntak, who defined what they called a one vertex magic vertex labeling, which has now sort of been commonly referred to as distance magic labeling. So the idea here is that we're going to label the vertices of a graph with the set 1 up through n, and remembering being the number of vertices. So as a bijection, so we're not going to repeat any of those labels. With a property that there's a constant, right? And what we usually call the magic constant k, so that if we add up all the neighbors, open neighborhood, right, of any vertex, we get the same sum in every vertex. And so if we're looking at this graph here, we'll see, right, that, for example, this vertex labeled 2, right, its two neighbors are 4 and 1, so it would have a sum of 5. And so would this vertex down here in the corner, 1, right, its two neighbors are 2 and 3, sum of 5. 3 has neighbors 4 and 1, sum of 5, right? So the things that are distance 1 away, right, all have the same sum if you add those things together. So this is kind of the sort of foundational definition of what I've currently been working on, is this on an undirected graph, this idea of distance magic. And so that's kind of the sort of starting definition. And so as I think about algebraic sides of this question, in 2013, Dalibor-Franchek defined group distance magic labeling, right? So instead of doing that bijection from the vertices to the set 1 up through n, right, you can define that bijection to be from the set of vertices to an abelian group of order n, right? So it's still a bijection, and then you sort of, add, or what operation you might be, at every vertex, right, the weight of everything that's its neighbor, and that thing still has a magic constant. So same idea, but just using a different set of labels, and then obviously different potentially operation depending on what group you're working with. And so note that obviously in a distance magic labeling, if you already have a distance magic labeling, then you also already have a Zn distance magic labeling, right? If you just mod everything by n, then of course you're still going to have the property that you had originally, since we were adding before, and we're just doing the under modular arithmetic. The converse of that is not true. So you can create some graphs. And I think in this first paper in 2013, Dalibor has an example of that. It's some cycle products of graphs that are not distance magic, but they are Zn distance magic. And so there is some sort of interesting relationships here, sort of, right, this sort of one implies the other, but not the other way around. So from that, the work that sort of I've been doing recently, I like to label directed graphs. So I like to take a definition and say, let's see what happens if we do that on a directed graph. And a lot of this stems from, again, some older sort of concepts or ideas. And so H-flows is probably the sort of, original sort of labeling of things. And in H-flow, we usually are assigning labels to the edges. There's no restriction on repeated values in an H-flow. And so that at every vertex, right, the things sort of coming in should be the same as the sum going out. And so it has a similar kind of idea that we're going to be using to help define this definition for us in the directed case. In a similar sort of way, Slater and others defined conservative graphs in 1980, where again, they're labeling the edges, but strictly with the, distinctly with the integers 1 up through m being the number of edges. And so, right, that there would be an orientation that exists where the sum of the edges coming in would equal the sum of the edges going out. So a type of flow in a sense, but requiring, right, that we use distinct values from 1 up through m. And then I have a similar definition from work I did in my dissertation where I'm starting with a graph that already has an orientation. So I'm not looking for an orientation, and my graph can have bidirectional edges with a similar sort of question, labeling the edges so that the sum in is equal to the sum going out. So these things obviously have some sort of relationship. And then for us thinking about this, what we wanted to do was think about how to do this on an oriented graph. And so again, I want to give you the sort of algebraic definition that helped, again, motivate this current question that we're working on. So this is the sort of algebraic sort of idea of what we took from distance magic, right? And thinking about how to do that on a graph that might have some sort of orientation or direction. And so here we're labeling the vertices again with the elements of Zn in this case, but you could obviously replace that with your favorite abelian group. And so this is Zn, so that the sum of the vertices going in minus the sum of the vertices going out is a consistent weight across all vertices. And so if you look at this C3, this is actually a graph that is not distance magic. You cannot make this a distance magic graph, but you can sort of look here, right? If we look at this vertex 2, it's got 0 coming in, it's got 1 going out. So this would be equal to 2, right? In our sort of mod 3 world. And over here, same thing, 2 coming in, 0 going out. And down here, we've got 1 coming in and 2 going out. So, or wait, 1 coming in. Yes, is that right? 1 coming in, 2 going out. That's -1, which is 2. All right. So this is the idea, again, the algebraic sort of side of what I'm going to be talking about today, but you can sort of think about these kinds of questions from this angle, which is labeling the vertices with elements of an abelian group instead of labeling them with 1 up through n. And so we'll see some of the relationships between these things today as we talk about examples. So in this Zn magic orientable graphs, these are some of the classes of graphs that have been studied. So they have sort of a large collection of things that you cannot do, right? Just based on if you have a group of order congruent to 2 mod 4, and if all the vertices have odd degree, that's a potential problem. And that comes from the group structure of thinking about abelian groups that will always have a Z2 as a component. And then circulant graphs, various products of circulants, lexicographic products of various graphs, complete graphs, if and only if n is odd, bipartites, if and only if the parts are even. They've looked at some other multipartite graphs. So these are some of the kinds of things. I just wanted to do a quick summary. Again, this is not my specific area that I work in, but I wanted people to kind of see what people have done in the past. So the work that I've been doing recently today that we're going to talk about has been work that I've been collaborating on with Brian Freiberg at the University of Minnesota Duluth. And some of it is hot off the presses. I just finished 4 weeks of research with 4 students at Southwestern, 4 undergraduates. And so we just spent 4 weeks working on some of the questions that you'll see here today and what we're going to talk about. So this is my group of collaborators: Emma, Lauren, Catherine, Rowan, myself, and Lauren Russ. We were all kind of working on this. Lauren Russ, I guess 4 students and a faculty spouse, I guess, joined in on the fun there. So that's Lauren Ross as well. So that's some of this work you're going to see over the next few slides comes from work I did with Brian and or with these students over the last couple of weeks. So this is a definition that Brian and I sort of wrote down after a talk I gave at a conference and sort of collaborating between sort of what he does and what I do. And so the idea here was to take that Zn orientable definition and sort of use it in just taking the labels to be 1 up through n in standard addition subtraction. So here, right, we're talking about the weight of the vertex to be the sum of everything coming in minus the sum of everything going out. And we want that to be the same magic constant, right, across all vertices. And if there is a distance magic labeling, then we're going to call this graph to have a difference distance magic directed graph. So DDM, DG, you'll see that. And we might talk about DDM as an abbreviation throughout this. And one of the first questions we sort of thought about is like, well, what can this magic constant be? And it's very interesting. In this case, it has a very specific value that it can be. And in particular, if you sum over all the vertices, right, you would add up all the weights everywhere, right, then you would have the magic constant at every single vertex, and they're in vertices. So that full sum would be n times k. But if you sum the weights, every single vertex will appear exactly once as a positive value and as a negative value, right? Because every vertex is going to be, right, the end or the beginning of some edge. And so every sort of edge, right, will account for both a positive and negative value at some point. And so if you add up all those weights, you're going to get 0. And so n times k would equal 0. And in this case, n is a positive integer, because we are in the integers 1 through n. And so in this case, k has to be 0. It's the only thing that can be 0 in that equation. And so in fact, we could alter this definition to say what we're really wanting to do is label the vertices, right, in such a way that the sum coming in is equal to the sum going out, right, of the neighbors of that vertex. So we started out with this difference distance magic labeling. That's kind of what we were calling it. And then we later realized that, in fact, the difference isn't that important. I mean, the difference has to be 0 in this case. So really what we're wanting is for the sums in to be equal to the sums out at every vertex. That doesn't mean that those sums are the same at every vertex, right? So it could be that one vertex has 7 coming in and 7 going out, and another vertex has 6 coming in and 6 going out, right? But that each vertex, the amount coming in and the amount going out is the same. So that's kind of our definition that we're going to work through in this sort of first section, and look at some of the sort of initial results we have in this area. And so comparing it back to some of the definitions we gave earlier, right? So an oriented graph may be Zn distance magic. That's the, but maybe it would not have a difference distance magic labeling. And so C3, the example we saw there, you cannot label that as a difference distance magic graph. And we'll talk a little bit about why in a minute, but there just aren't enough edges to make that happen. So these are sort of larger in class in some sense than those. Any graph that is DDM, you can create a Zn distance magic labeling, just similarly to the undirected case, right? If you just mod by n, the property will still hold. If the sum coming in and sum going out were the same before, they will still be. So that's the other direction, I guess. If a graph is distance magic, it may not have an orientation that is difference distance magic. So C4 is an example. We saw that on a few slides ago. In the undirected case, you can create these distance magic labelings, but you can't find an orientation that will give you a difference distance magic labeling. But you know, there are some distance magic graphs that can be oriented to produce a difference distance magic graph. And so here's our sort of first example of one with this definition. And so, right, if you look at each vertex, I think here at the top, right, the sum coming in minus the sum going out this is 5 and 5, right? So that's good. Here we've got 5 coming in, 5 going out, right? And then same thing. I think these are all 5s in this case. 5 in and 5 out at each vertex. And then in the middle here, we've got 5 in and 5 out. So this is one where the amounts coming in and the amount going out are the same at every vertex. But we'll see some examples later where that's not the case. But this is an orientation, right, of a graph that does have a distance magic labeling in the undirected case. And we're also able to find this orientation that produces a difference distance magic graph and for our sort of definition. So some things to note, because of the fact that we are using distinct values, and we're not allowing repeats, we must have at least 3 edges incident to every vertex, and we can't have a sink or a source, right? So a sink or a source would be bad, because then there would be a whole bunch of stuff coming in and nothing going out. And in this world, right, if we add a whole bunch of things, they cannot equal 0. So similarly, right, if you only have 2 edges coming in or out of a vertex, and so one's coming in and one's going out, because we can't have sinks or sources, then that would imply that wherever they came from, those things would have to be the same sort of value, right? You have to repeat values, and we can't do that. So that kind of gives us a sense like that eliminates a lot of those small cases. We can't have sort of small things in an oriented graph. That's in the oriented graph case. If we allow for bidirectional edges, then you can have 2 edges at a vertex, right? One coming in and one going out, like as part of a bidirectional edge, because it just adds and subtracts the same thing. So it's sort of like this amount coming in, amount coming out, sort of cancel each other. So if you only have bidirectional edges at a vertex, then you can certainly have 2 of those only. It's sort of, we'll see later, those examples maybe aren't very interesting, but you can do that. Sort of the trivial case that we'll kind of not necessarily talk about when I talk about whether something exists or not is if you take any graph and just put all bidirectional edges on it, then certainly the amount coming in and the amount going out are going to be the same, since what's coming in is exactly the same as the amount going out with those bidirectional edges. And so those are sort of, we call like trivial examples, right? So take your favorite graph and make everything bidirectional. So those are out there. We won't usually talk about those as interesting, but know that those are the case, right? For any graph that you want to create. And another sort of interesting property here, you can take an oriented graph, for example, and then any two vertices that are currently not adjacent, you could add bidirectional edges between those, right? And it would become a directed graph that has this property. And similarly, if you have bidirectional edges on a DDM GG and you take those away, right, any number of them, then what's left should still be, right, still have this property because you're removing the same values, right, coming in and out. So this is really kind of interesting to start thinking about, well, like if I think this is going to work, right, I should be able to remove all those bidirectional edges, and what underlies, right, should still have this property. And so that immediately tells us some things about what we can do and what we can't, because they still have to have those like enough edges everywhere, right? We might end up with some isolated vertices, but it sort of helps us kind of think about what sort of structures we can and can't have as we sort of build these properties. So with those two sort of last two facts on that previous slide, we know that we can't do sort of any path or any cycle because there just aren't enough edges, right? If you start to think about duplicating edges, right, and sort of going both ways, except for the trivial case where everything is bidirectional, you won't have enough edges again, right? Like, because if you can do any one of those, right, you should be able to remove those bidirectional edges, but then if you remove bidirectional edges, you'll end up with vertices that don't have enough edges. And so some of those sort of starting classes that a lot of labelists like to start with, I guess they start with these small classes, but these don't work for us here. They just don't have enough edges. And so we have to think a little bit more interestingly about like, what are those sort of first or sort of smallest cases for us? And so this is some of the work that our students that I just worked with over the last 4 weeks were working on. And they said, well, what are some of the smallest non-trivial examples, right? So if we start thinking about these graphs, and so nothing with 4 vertices works except for everything that has bidirectional edges. And so we started looking at sort of 5 vertices, and Lauren Ross sort of was asking questions about like, well, what's the possible values for the in and out sum, right? Like if I look at vertex 5, right? Like vertex 5, the most it could have coming in, right? 4, 5, 6, 7, 8, 9, 10, right? Would be everything coming in or something, right? And that would be 10, right? So that's like the largest sort of in sum for 5, right? And I guess the smallest in sum would be 1. And so those are all the possible in, which also are the out sums, right, at vertex 5. And so like sort of examining each of those cases, right, from 1 up through 10, and a lot of them are eliminated pretty quickly. And so it turns out that these 3 examples here are the only 3 sort of examples for 5 vertices. So the same graph, right, these are all the same graph, a couple of different orientations of this wheel on, I guess I call it W4, with 4 vertices on the exterior. And so these are kind of our smallest examples of DDMOGs. So difference, distance, magic, oriented graphs. So no bidirectional edges here. In this example, we'll talk about adding those in just a moment. But yeah, so these are the first few cases for v equals 5, and doing a similar kind of process of examining the possible in and out sums at vertex 6. We also have these examples here, right, as the sort of 6 vertex graphs. And so these are the only oriented graphs on 6 vertices that also have this property. So again, sort of 2 underlying structures with slightly different orientations. Right, and so again, you're looking at each vertex, but the sum coming in should be the same as the sum going out. And these ones are maybe slightly more interesting because the sums aren't the same everywhere. I think like if we just take a quick look at one of these, I think if we look at this example down here, maybe this one has 3 coming in and 3 going out at this vertex, right? But then this vertex down here has 9 coming in and 9 going out. So they're not the same everywhere. And so that's kind of interesting. These also aren't all regular graphs, which I think is nice. When we have these sort of non-regular examples, those are ones that are kind of more interesting to sort of look at and think about like how we can like generalize those to find other non-regular families. And so this is sort of just a starting space of sort of getting some small examples. Starting to look at sort of common classes of graphs, it's not really possible to orient a complete graph, assuming you have at least 2 edges, to make it difference distance magic. And if you're thinking about that, right, like as soon as you have 2 vertices, if you add up all the remaining vertices other than that vertex that you're looking at, you're always going to end up with one sum being even and one sum being odd, as long as you have at least 2 vertices. And so if the sum of the remaining values is odd, right, there's no way to have half of those, right, sort of be the in values and half of them be the out, right? In a complete graph, everything has to be connected to everything else. And so if you have an odd sum, right, you can't split that evenly into some of those things coming in and some of those things going out. And so we can't do any of the complete graphs, right, because there'd be some vertices that would never allow this opportunity, right, for half the things to come in and half of them to come out. And so we have this interesting sort of question sort of still lying around, thinking about how many like bidirectional arcs do I need to add to make that complete graph have a distance difference magic labeling, or can I even do that? So for small ones, K3 and K4, it doesn't matter, right? We have to sort of add all of them have to be bidirectional before it will work, right? That sort of trivial case, right? So K3, we have to add all the edges have to become bidirectional before it has this property. Similar for K4, you have to add all 6 edges be bidirectionals before it becomes difference distance magic. But for K5, you only have to add 2 bidirectional edges in order to have everything connected, right? And have this property. So if we go back just a little bit to these wheels, right, you can pick your favorite one. And there's only 2 sets of vertices that currently aren't connected, right? In this first example, 3 isn't connected to 2 and 1 isn't connected to 4. So you could add bidirectional edges between those, right? And then you would have a complete graph where everything is connected to everything else, either by one edge or edges going in both directions. And so this is kind of a fun little thing for us to play with, is like, well, if we can't do it, right, can we do it if we add a certain number of bidirectional edges, and sort of what's the minimum number of those that we need to add? Is sort of a fun question that we didn't really have a lot of chance to explore this summer, but I think is sort of interesting to sort of think about if you're thinking about sort of making this happen as early as possible with adding up some extra bidirectional edges. Another thing that my students looked at this summer was the wheels, and we can only do those if n is equal to 4. So you've seen those wheels. Those are the only wheels that work. In this case, Wn for us stands for n vertices on the exterior with a vertex in the center. So a total of n plus 1 vertices. And if you're thinking about this graph, since on the exterior, right, those vertices all have sort of 3 edges. So the sum of the values of 2 of its neighbors has to equal the value of its third neighbor, depending on how you orient the edges on that exterior. And so what you can do is sort of create a list of equations by taking pairs, sums of pairs of distinct numbers. You only have the values 1 up through n plus 1 available. And then their sums have to be something between 1 and n plus 1, because, right, you're only using those values as the labels. And so what comes in has to equal what comes out. And you're doing 2 numbers and 1 number. If you make a list of all those equations, you can do some interesting math to realize that no one integer is present in more than n minus 1 of those equations, either on either the addition side or the equal sign. And so that sort of hub vertex, the one in the center, it's a neighbor to every one of those outer vertices. So it would appear in every single equation of those n outer vertices. And once n is greater than 4, none of the vertices share the same neighborhood. So these are all like distinct equations. And so we would need that vertex value to appear in n equations, but at max, any number can only appear in n minus 1 of those equations. And so we just don't have enough sort of numbers to label this wheel in that way. So it's kind of an interesting sort of situation where, again, I don't know if it's possible. We sort of started talking about this at the end of the semester or end of the 4 weeks. Could we direct some edges bidirectionally and make this happen? And or could we add some isolated vertices so we'd have more numbers available or something to make this happen? And so I think those are some questions of ways to see if you can make this happen if you allow for certain structures that are not currently present. But in the oriented case, this is the only way we can do this, is with n equals 4. So it's kind of nice. This is where I got tired of drawing pictures. And so I just drew them by hand. I was like, we're going to draw these because the students were working on this sort of last minute, but they were working with a lot of different classes of multipartite graphs. And so I just wanted to kind of talk a little bit about some of those examples. And again, we have orientations if and only if S is even. This is similar to the ZN. So this works, it works there, but because it works there, it doesn't mean it works here, but it does happen to work here. So I guess it now means it also works there. So, right, if we figure this out, then it works for the ZN, but if the ZN figures it out, it doesn't help us. So, but anyway, so it works for us as well. The even ones are interesting. They're slightly different depending on if n is congruent to 0 or 2 mod 4. The 0 mod 4s are pretty nice. Like you just pair up your numbers, right? Everything comes in pairs, like this case in every pair is of 9. And then you can orient edges, right? Like this pair is going to go here and everything here is going to go there. And then this one's going to go here and everything here is going to go there. So it's kind of 9 in, or, 9 in at every vertex and 9 out at every vertex because you have all these 9s. And so you can kind of pair things up. When it's congruent to 0 mod 2, you got to do a little finessing, but you kind of cut your set in half. And then with those halves, each half kind of has the same sum on the left and each half has the same sum on the right. So you can kind of direct them again, where this is like 11 is going to come in, right? And 11 is going to go out if we send it this way. And then similar kind of with this process here. So it's kind of putting these things together in sort of groups and making that sort of happen. So those are kind of nice. And then we played around a little bit with bipartites where they're not equal. And so this was some of the last minute things that they were trying to write up. So I was trying to look at some of the examples, but this one's fun. This is like a 4, S. So you can put anything you want over here as long as it's congruent to 0 or 3 mod 4. And so you put like a big number here, and this is sums to 11, this down here sums to 11, and then these two sets sum to the same thing, kind of by getting a 10 and then a 10. So that's kind of nice. And then you can direct again, same thing. So this goes here, this goes out, this goes here, and this goes here. So kind of directing everything within those circles to each other. And then this is like these sort of H4P would be like 4 parts or 4 vertices in P parts. So we can do that for however many parts you want. So this is 4 vertices in each part with 3 parts. This is H4P3. And again, it's just thinking about those pairs. 4s are lovely. Anytime you have a 4, you can pair numbers up and then you can just kind of orient the edges in a certain way so that you get the same, that sum of 13 in this case comes in and comes out, comes in and comes out, comes in and comes out at every vertex. And it's sort of really nice. So we can definitely do various types of multipartite graphs. We're kind of working on writing those final ones up. I think we have a few more cases, but this is just some of the ones to show you kind of this concept of sort of thinking about parts and thinking about that. When Brian and I first started this work, he is motivated by thinking about tournaments. He likes to think about sort of these kinds of tournament questions. And so, if you have not seen sort of work in these sort of tournaments and labelings before, an equalized incomplete tournament of n teams with r rounds, right, means that every team plays r other teams and the total strength of the opponents is m for every I. So in other words, finding an equalized incomplete tournament is the same as sort of finding a distance magic labeling of an R regular graph on n vertices, right? So every team is playing R teams, and right, the sum of all their neighbors, right, is the same. So that's this distance magic idea. And so Brian is sort of motivated by this idea. And so one of the first things we sort of thought about was how we could convert that into this oriented case. That's the question he came to me with. And so we'll think of these vertex labelings that we do on this directed difference distance magic labeling as the team rankings. Any edge that goes from X to Y is meaning as game's going to be played between X and Y, where X is going to travel to Y. So we're adding this sort of travel piece to the tournament, right? Like sometimes we just talk about a team playing X playing Y, but now we're going to talk about X is going to go play Y at their particular home venue. And so in a difference distance magic sum, the sum of the ranks of the teams played at home is going to be equal to the sum of the ranks of the teams played away. So it's slightly different than this just general tournament structure where we actually are taking into account where you're playing. We think that's sort of interesting. So we have called these home away equalized tournaments. Hates, I don't know. I don't know what that word says, but so home away equalized tournaments is kind of what we're thinking about. And we will allow so provide bidirectional edges, which creates a scenario where maybe a team plays both at home and away with another team, right? Which often happens if you think about sort of conference play, right? Some teams play just like once within a conference, but like teams that are within like a subconference often play both at home and away. And so that allows for those bidirectional edges, which we sort of like having. And so we have a few examples of these. And again, we're trying to relate this back to, I think, the idea in the undirected case. But so if we have a graph that sort of has 2 mod 4 number of I guess M is a number congruent to 2 mod 4, and K is greater than or equal to 3 is an odd number, then we can create sort of an R regular difference distance magic digraph of order N, which is M times K. So it's an even value, right? But it's a sort of a certain even times a certain odd. And we can do that for values of R that are 2K, 2K plus 4, 2K plus 8, right? So all the way up to whatever, 2K plus M minus 6. And so the idea is to use these sort of like magic rectangles of sorts, where you have sort of over here on the left, like, right, each of these sort of rows sums to the same thing. I know 15, 16, whatever that is, 52 maybe, I don't know, 30, no, 30, 42. So all of those sum to the same thing, and same thing on the right, these all sum to the same thing as well. So we have these sort of two sort of rectangles that where the sums are all the same horizontally. And so what we can do is take one of those, right? Like take this set of numbers, right? And we're going to put that here as sort of 3 vertices, right? 1, 15, and 26. And then these are sort of what we're calling the complements of those values. It's just sort of the total number of vertices, right? Like the opposite. So 1 and 54 sum to 55. So we'll take the 3 opposites of those and put them in this sort of collection of things, 54, 40, 29. And then if you just orient the edges right around in that sort of cycle, right, everything in this group is directed to everything here is directed to everything here, then since every other set has the same sum, these sums aren't the same, right? The sums in the left are not the same as the sums in the right, but what's coming in will be equal to what's going out because you have the same sums on either side, right? So at the complement side, anything that's in that complement set will get, in this case, 42 in and 42 out, right? And anything that's not in a complement set will get whatever the other sum is, right, in and out. And so that creates that sort of 2K regular version. And then because of the sort of structure of things, you can start adding sort of 4 things. When we count regularity here, we're just counting total adjacent, like number of edges coming in or out. We're not paying attention to that direction. But you can take something like 1 and 3 and 54 and 52 and sort of direct these things this way. Sort of 1 is going to go here and here. So 1's going to go to 55, sort of, and sort of you can create things. So we'll kind of go here, sort of 2 things here. You can kind of create this sort of structure internally. We're kind of creating these circulant kind of graphs on the inside. By sending things like in sets of pairs to like skipping over so that you don't repeat edges that are already there. But like 1 could go to 3 and 52, so that's 55, and then 3 could go to 5 and 50. And so you can kind of create this sort of structure where eventually you're adding 4 edges to every vertex, right? And then you can do that again by sort of skipping a certain other number, right? Kind of like rotating your skips around to sort of create this a graph that you can keep changing the regularity, right? Depending on how many games you want to play in your tournament, right? Like 2K, 2K plus 4. So you can add by 4 and sort of create this sort of structure, which is kind of fun. And then another option, if you want to do this with N being congruent to 2 mod 4, you can do a similar sort of thing, right? Where you pair up the highest and lowest, right? And then everybody's got the same sum of 1 and 10, 2 and 9, 3 and 8. So there's sort of 2 vertices in each sort of larger group. And everything here, right, is everything in this 1 and 10 is connected to 2 and 9, right? So there's really like a whole bunch of edges here, right? I guess 4 edges, 1 goes to 2 and 9 and 10 goes to 2 and 9. And then, so right now, everything coming in and everything going out is the same. And you can certainly add, this is, you could certainly add this if you wanted to, right? Like this sort of interior, so you can add, more if you wanted, you could add that in, right? And create another round of tournaments. But if you wanted to get something where R is congruent to 2 mod 4 at any point, you can obviously keep adding these. This is always going to add, the interior cycles are always going to add 4 each time. But if you want to like change it into something that's congruent to 2 mod 4, you can always add these bidirectional edges, right? Where they're playing each other. And then you go from, having 4 in and 4 out, right, to 6 in and 6 out, or from 8 in and out, or 8 sort of total degree to having 10 total degree. So it's like a way to sort of get some of the different values, right, that you might want by sort of doing some of this this sort of bidirectional edge stuff that we haven't really allowed in other sort of labelings that people have done. So, so that's kind of another sort of angle of this. That sort of was the work that Brian and I originally started. We got distracted by another problem. And so haven't come back and finished up this work in a while, but hopefully with some of the work that we've been doing recently, we'll come back and finish this one up as well. So it's kind of like the difference distance magic sort of labeling that I wanted to talk a little bit about. I have one other type of labeling that actually was sort of the one that inspired this one. So I'm kind of going a little bit in sort of a backwards way today, but I want to talk a little bit about one other type of labeling, and then give you all a chance to ask questions, and sort of talk a little bit about if you have some questions you want to ask. So D-magic labelings are another type of labeling that I was been working on. And so this sort of definition is a similar definition to what we saw before. Again, this is the undirected definition. And here, it's the same idea. We're going to label the vertices one up through n. That's what I like to do with as the bijection. And we're going to look at D distance magic labeling, where D is a distance set, right? So D is any number from 0 up to D, D being like the largest distance in the graph that you have in front of you. And you're going to say, right, it's going to be D distance magic. If you add all the things that are D distance away, right, you get the same value at every vertex. So instead of the one vertex, sort of one distance away is what we just did, right, where everything we were just looking at the one neighbors, right, what's one away. But you can generalize this and just say like, what's D away, right? Like, and make D be a set of whatever your favorite distances are. So in this example, this is a 1-2 distance magic. So if you go to any vertex and count sort of what's 1 and 2 away, in this case, that's 6, right? Or I guess 6, 7, this is also 1 and 2 away. I always think of orientation. So 6, 7, 8, 9, what is that? 14 maybe? So 4, 5, 6, 7, 8, 9, 10. Yes, 14. So I think we have 14 here. We can go to another vertex. We should get the same no matter where we are. We can come maybe here at 2. We would have 1 plus 3 plus 4 plus 6. That is also 14. Right. So we're looking at things that are 1 or 2 away, right, from a given vertex and adding those things together. So if we look at 4, right, we'd get 2 plus 3, 2 plus 1 is 3, plus 5 is 8, plus 6 is 14. So this would be 14, right? So at any vertex, right, if we add the things that are distance 1 or distance 2 away, right, we would get the same sum at every vertex. So it's just a slight alteration of that standard sort of distance 1 away. And so this question really sort of came about like that has been around for a little while, since 2011 for the D distance magic. And in 2008, I had been working on, as part of my dissertation with my advisor, Wal Wallace, and Gary Bloom was also part of this work. We had defined magic labelings on directed graphs, right, which is taking a graph, right, and directing the edges in such a way that the sum coming in at every vertex plus the label on that vertex is equal to the sum going out, right, plus the label at that vertex. So I think in this picture, we have 15 at every vertex. So if you take the edges coming in, right, in this case, 5, 3 is 8 plus 7 is 15. And then if you take everything kind of going out, right, with that vertex label, so 7 plus 6 plus 2 is also 15. And then you should be able to have that 15 everywhere. So this was kind of one of the first, I think this was the first sort of magic labeling on a directed graph. And so this was sort of work that I had been working on, was magic labeling and directed graphs. My colleague, Rino Simanjuntak at the Institute of Technology in Bandung, Indonesia, was working on D-distance magic graphs. And so in early spring of 2022, I had a sabbatical in spring of 2020. I went over to Indonesia in January and February of 2020 and did some work with Rino on sort of combining our two passions, right, of my things with magic directed and her sort of D-distance magic. And we created this definition for D-distance oriented graphs. And so this labeling, right, D-magic labeling is taking the vertices of the graph, labeling them 1 up through n, right, where if you look at the things that are D distance away, right, they have the same sum, right, the neighborhood, the D distance neighborhood, we're going to call that, right, they'll have the same sum. And we're looking at the orientation now. So the D distance, like you can actually move in that direction, right? So we're following the directions of the arcs. And so here's a great example. This is a 0-2 magic oriented graph. So if you take any vertex here, this vertex, right, the things that are 0 away are obviously the label itself. There is nothing 2 away from this top vertex. So this total sum here is 10. But if you come to this vertex here, 5, right, and take 5 being distant 0 away, and the things that are 2 away would be 1 and 4, right? So +1 + 4, we get 10 here, And you can pick another favorite vertex, maybe this one, right? 8 plus the things that are 2 away. This is the only thing that's 2 away. We get 10. And you can pick your favorite vertex, right? And everything should have distance 0 or 2 away, summed to 10. And so if G is D magic, you can have at most one sync, right? And if you have that sync, then you have to have 0 in your distance set because it has to have something that it sums to. And in that case, the magic constant would be n, the total number of vertices. The magic constant can vary in these graphs. There are some magic labellings where the magic constant has to be the same at vertex, depending on the kind of graph. But here, for example, are 2 different graphs, same orientation, but with different magic constants. So just be aware that when we work here, the magic constant is not unique, and there are some labellings where that is an important feature. So here is a nice class of one distance magic oriented graphs of order n. So you can add as many vertices as you want. You can have whatever magic constant you want between 5 and n. If you kind of create the structure where you put that k kind of in the center, have the larger values below it, and then kind of orient the edges up top, you can create something where the magic constant is k. So if you think about things that are 1 away, in this case, right, the things that are 1 away from k are always going to be these. Right, this one is exactly 1 away from just k and just k here, right? All those larger values, and then up here you kind of fix up the top values. Everything in the middle is already k away, 1 away from k, but then you just have to fix kind of the outer 2 vertices. So you can kind of create this like whatever you want of any size, which is kind of fun for one distance. You can do trees with only one sync, have to have all the edges directed towards that sync. And so there's a proof by contradiction in that you'll eventually have another sync. And so trees with n greater than or equal to are not going to be D magic for any distance set D because of the direction of those edges. So trees will have that exactly one sync by the sort of correlate, I guess the lemma up there, and all the edges are going to be directed towards that sync, which means that 0 has to be in the distance set and your magic constant is n. And so the longest path of length D will end at that sync. And 0 is in your distance set, but little d is not in your distance set. And so anything less than D can't be in the distance set. And so your distance set only contains 0, which I guess that's not going to happen if you have more than one vertex. And so, yeah, so we can't do any kind of trees, I guess, except for the single vertex, if you think that is interesting. And so that kind of eliminates a big family of graphs that people like to label. Again, we played with some multipartite graphs. This is K and N. You can use various different distance sets. You can use the set 0, 4, 1, 2, or 3, or any sort of union of those individual sets. So you can pick your favorites of those, because if it's magic for one of these sets, it's magic for all of them. So you can sort of play around with that. So this is kind of an example of that. Using some sort of things we know about how to partition sets, you can sort of create multipartite graphs that have this property. And so that's also very nice. And then you can also take those multipartite graphs and remove a 1 factor. Cycles are a fun case. If there is going to be a D magic labeling, then it's going to be unidirectional. That's the only way that it's going to work. Any other sort of situation, you're not going to happen. And you can find a distance set that Cn is D magic for all n greater than or equal to 3. Certainly D equals to 0 up through n-1 would work, because those are all the distances, right? In a unidirectional cycle, everything is distance between 0 and n-1 away. But you can also create distance sets that are divisors of n that would also work. So like in this example, you could certainly create a labeling with 0, 3, for example. That would be one that would definitely work here in this C6 example. I think I put the values there for this is, I think this is 0, 3 magic now, if we look at this. So if we look at this vertex, 1 plus 3 is, let's see, 1, 2, 3, 1 plus 6 is 7, 2 plus 5 is 7, 3 plus 4, right? So everything is, if you look at the distance 0 or 3 away, every sum is going to be 7. If it's 0-3 magic, it is also 1-4 magic, and it is also 2-5 magic, right? Because you're just shifting over in this unidirectional case. So you can also say that it's all of those things as well, which is sort of nice. Yeah, so I kind of went through that last bit a little quickly just to give some time for questions, but some things that, you know, I think are interesting in the first labeling that we talked about are like, when can those bidirectional edges or isolated vertices help us? You know, you can also work in other, so the work that's been done there has mainly been in ZN, but, you know, you could potentially ask questions about how to label these things in other abelian groups, right, other than ZN. And in D magic, right, again, there are a lot of sort of open questions there as well. But I don't think anybody has really done much work at all in D magic with any sort of abelian group. So I think this idea of labeling with, right, elements of an abelian group instead of 1 up through n could be answer some interesting questions maybe about distance sets that are different than just 1 away, right? Which is sort of the standard sort of examples that we see. So I'll stop there and allow you all to ask some questions if you have any. Thank you.
Thank you. So is there any question for Alison? Okay, so if there's no question, can I ask one? I just wonder, like, have you done any work with graph with like small diameters, say like diameter 2, or I feel like it would be the easy case if you, I don't know if it's gonna be easy or not. It's just like, I feel like it's reasonable to think about, because if you have diameter 2, you kind of have to use all the vertex. I saw, yeah.
Yeah, I think that's an interesting question. We haven't talked about, like, right, like, yeah, graphs with diameter 2, right? Then you don't have a whole lot of options in that last, the D magic case, right? Like for what your distance that can be. So yeah, but I think, you know, you have to think about what the orientation, right? I think that's what's always a little interesting to me is like, once you orient the edges, like what is, yeah, like diameter 2, right? Like what does that mean? And so like thinking carefully about that, because it may have diameter 2 in the undirected case, right? But
oh yeah.
Once you orient the edges, then it changes, right? So
yeah.
I mean, yeah, I think it's an interesting question. I think you could still do it, right? But you have to be very careful about the orientation. And so I think once you orient the edges, a lot of times you also end up with the diameter is sort of infinite, right? In a lot of cases, because you can't get somewhere, right? If you orient in a certain way. So it's a little tricky, but you could maybe start with graphs whose underlying graph has a diameter of 2, right? And ask that question. But yeah, once you orient the edges, it may end up that you don't have finite diameter, right? So it's
yeah. Okay, thank you.
Can I ask?
Yes.
Thank you. On one of the previous slides, you had the restriction of lowercase n, the sum of n's to be n, so n1 to ns being n. Yeah, 3 slides. One more. Yes, over there. Yes, the last one. N equals n1 to ns, and k has an orientation that is the magic. And what does that restriction mean? N equals the sum of those n's.
yeah, let's see. So let me see. This is one I haven't thought about in a little while. So let's see. So what this means, I think, is so we're going to take a set n, and we're going to break it into s parts, and each part has a size, right? Like n1, n2, all the way up to ns. And so those are the different sizes of those, or those are the different sizes of those sets, right? And so if you take a multipartite graph, maybe the first one's got 7 pieces and the next one has 3 and the next one has 5, right? Or whatever. So those are what the little subscripts, I think, right? Those are just different sizes of those sets. As long as, you know, n times n plus 1 is 2 times s times t, and t is some number bigger than n.
Yeah, I think this solves the problem of counting the number of unordered non-negative integers constrained with the sum.
Sorry.
I think, but there is no solution known for now, but I think this solves it because, yeah, actually, my expectation is that this difference distance magic can be used to solve this problem. Because right now the computers use the iterations, and there can be a lot of iterations, and it takes a lot of time. But if you are able to compute the number straight by some mathematical formula, that will be a massive time saver, I think.
Yeah.
Yeah, thank you.
Thank you.